Hello everybody. In today's video we're going to be covering electric fields. Now in the last video we talked about how charges apply a force over a distance. This is referred to as Coulomb's law. It is given by that formula we picked up. The electric force is equal to K, Q1, Q2 divided by R squared. Now what the electric field is, it's our method to show how a charged object affects other charged objects around it using that electric force. So we're going to be looking at exactly what this looks like, why we use this method, or why we talk about electric fields in the first place, why that can be helpful. Now, it's important to note that electric field exists anywhere where there is an electrical force acting on a charge. So this charged object over here would be giving off an electrical field, and this charged object over here would also be giving off an electrical field. Now, the definition of an electrical field, the mathematical definition, is the force over a charge, which is the electric field will allow us to figure out the force of an object by seeing if we know what the charge on that object is. It's also important to note that it is a vector, so it does have a directional component to it, and we're going to be seeing that a lot because we're going to be drawing a lot of different pictures showing these field lines, and we're going to be using arrows to represent them. Now, electric field lines are probably the most common way we're going to be working with electric fields. These are imaginary lines that show what a positive test charge would be forced in an electric field, or which direction would it be pushed or pulled in an electric field. So what I mean by that is, let's say we have this large charged object over here, and it has an electric field around it. If there is another charged object around, it will be pushed away from it because charged objects, both positively charged objects, repel each other. So if we were to put some very small test charge, basically something to allow us just to see or feel the electric field there, in an area, what these arrows would show us is which direction that charged object would be pushed. So in this case, if we have a charged object and put on this arrow, it's going to be pushed to the right. If we were to put one over here, it would be pushed upwards to the left, and so on. So what these electric field lines show us is which direction they're going to be pushed, or in some cases pulled, depending on the charge of the object. So the charged object, the positively charged object, will always be pushed in the direction of the arrow. Now, there's some important things that these electric field diagrams show us. The first one is the distance between the lines shows us how strong the electric field is at that point. So if you recall, the reason why we show vectors, or the reason why we use arrows for vectors, is because it can give us two bits of information. It can tell us the magnitude and the direction. Now, for electric field lines, we're going to be changing that up a little bit. Rather than showing us what the magnitude of the electric field is based on how long the arrow is, instead we're going to be describing the magnitude of the electric field by how close together the arrows are. And the reason why is electric field lines are inherently, at minimum, two-dimensional drawings. So we really need to kind of come up with another way of showing how electric field lines work. So the closer together these lines are, the stronger it is. And we can see that between A and B. At point A, you can see that the electric field lines are closer to each other than at point B. And what that means for the formula, if you recall, this over here, that means that we're going to have a stronger force there. So we're going to have a higher electric field strength and a stronger force at point at point A than we would at point B, because the distance apart at point A is they're closer to each other, which means they're stronger. And this should make sense because point A is closer to the charged particle. You would expect a greater force than point B, which is further away from the charged particle. So we're looking at the distance between the arrows, which will tell us how strong it is at any given points. Now, let's look at a couple of different drawings for electric field lines. Now, we've already looked at a positively charged particle which would have arrows pointing in all directions, because if you were to put another charged object there, it would move away. A negatively charged object is just the opposite. Now, I kind of went by this very quickly, but in the last slide, we referred to as a test charge. And what a test charge is just a very small charge, again, that we put in an area that tells us, that allows us to see the effects of the electric field. We can't know electric fields there unless we have something charged to experience that force on it. So we use what we call a test charge, which is often just a make-believe thing, to allow us to basically see where and how strong these electric fields are. So if you were to put a positive test charge over here, what way is it going to want to go? It's going to want to go towards that negative charge. Now we can get more complicated, but it allows us to see a little bit more clearly how these work. You can imagine a positive charge here will want to go away from that positive charge. A positive charge over here would want to go towards that negative charge. You can see right in the middle, it's actually a straight line. Now, there is one important misconception that always comes up with these, and it's one that I had for a very long time, and it's what these lines are showing you. These lines are showing you which direction a test charge would get pushed. It is not showing you the path that a charged particle would take. So a positively charged particle that's resting, that's resting right here would get pushed this way, because that's where the electric field line, if it was over here, it would be pushed this way. Now, it does not mean that it will actually follow the path. It would not actually go up and around and back that way. For example, there's nothing over here. If I'm telling you that's being pushed to the side, there's nothing over here that's pushing it down, that's making it go this way at that point. So why would it make that curved path? Instead, again, what this is showing you is which direction it would get pushed, not which direction or not which path it would actually follow. Now, really, the exception to that is whenever we have a perfectly straight line, which we see in the center here. If you were to put a charge over here, it would both be pushed and moved in the direction of the arrow. Now let's look at a couple of other examples. Here we have two very positively charged particles, and you can see that they're pointing both away from each other. Now, if you remember back to the last slide, we talked about how close these field lines are, allows us to see how strong the electric field is. So at this point, very, very close, we have a very strong electric field. Over here, it's starting to get weaker. But if you look right in the middle, the electric field is infinitely far apart. Now what that means, and if you imagine a charged particle right in the middle, which direction would it go? If this charge wants to push it this way, this charge wants to push it this way, in the end those two forces cancel out, which means we end up with an electric field that is very weak to non-existent at that point. If you were to put a test charge right in the center, it would not have a direction it would want to go. Those two forces would cancel each other out. Versus if we look at this one, we can see that in the center, that's where it's closest. However, as you get more and more spaced apart, it gets further and further apart from each other. This is kind of the opposite over here. You can see if I have two negative charges, we end up with the same thing in the center. The arrows are just flipped. If I was to put a positively charged here, again, it would have no preference to go to the left or to the right. The same thing for this one over here. So the thing that I like to keep in mind when thinking about electric fields is what would a proton do? We often have to draw these electric field lines. And so when I draw these electric field lines, I try to think, what would a proton do at this very moment? If I have a negatively charged particle, what would a proton do over here? Well, it would want to move towards it. What would a proton want to do over here? It would want to move towards it. And if you do enough of these, you'll find you're just making the drawing that I have over here. Now, electric fields around point charges, we do talk about them. However, because they change over distance, they tend not to be too important for our calculations. We tend not to do too much work with them other than kind of acknowledge that, hey, they're there. These are some interesting properties about them. You get further away, they get more spaced out. They make some interesting shapes when you have multiple particles together. Where most of our time is going to be spent is talking about the electric field between two charge plates. And the reason why is because between two charge plates, all of the field lines are parallel with each other. That has some important effects. The main thing being is that the distance between them at any given point is the same, which means that the electric field strength at any given point, as long as you're in between the plates, is the same. So since this field is constant, the force on all charged particles is the same regardless of position. Because my electric field strength is the same, that will make my force the same as long as we're talking about a charged particle that isn't changing charge, which it wouldn't be. So these things stay the same. Now, this often, people often have a misconception. And it's very fascinating when I poll students. Half of them will say one thing, half of them will say the other, and almost no one will say the right answer, which is if I put a charged particle, let's say a positive charge over here, and a positive charge over here, which one, assuming that they're the same charge, which one would experience the greater force on each other? And the answer is, I just went over, it's the fact that they are the same as each other. And you can think about it this way. If this charged particle over here, yes, it really wants to get away from this positive plate up here. It wants to move far away from it. However, it's only slightly attracted to this negative plate because we got some distance between it. On the flip side, we have this one, which we have a negative plate over here. It really wants to get close to that negative plate because it's close by, and it only kind of wants to get away from this positive plate because it's kind of far away at this point. This distance, this is kind of a mirrored image of each other. That means you'll end up with the same force. No matter where you put this positive particle, the force above of repulsion from the positive plate and the force of attraction of the negative plate will add up to be the same thing. Yes, the negative plate has a greater attraction than it does on this particle than it does on this particle, but at the same time, the force of repulsion from this positive plate on this and this positive plate's greater, they end up canceling each other out. You end up with the same force regardless of position. Now, another question is, field lines never cross each other, and none of the drawings that we've done so far, they don't cross each other. Why is that? Again, what these electric field lines are showing you is which direction they would get pushed. So it doesn't make sense to have a charged particle that's being pushed. Let's say if I have an electric field line that's going this way and this way that they cross, what would an electric particle do over here? Well, this is saying it's being pushed this way, it's being pushed this way. No, you're only going to be pushed one direction. So you can never have field lines that cross each other. You're never going to see that because that does not happen. It doesn't make sense. What a field line, again, shows you which way they'd be pushed, and that doesn't work out here. Now, we've actually talked about gravity quite a lot before in the previous units. And like last video, gravity has a lot of similarities to electricity. And another thing is gravitational field strength. Gravitational field strength is absolutely a thing. It's something that we've worked with, though at least I haven't really called it this, though you may have noticed in the reference table, it is labeled as this. So just like an electric field, gravity has a field associated with it, the gravitational field strength. And the value for the gravitational field strength is something that we've seen before, and that is G. So G is the gravitational field strength. Yes, that G, 9.81 meters per second squared on Earth, or how we often, or another way of drawing the units for it, 9.81 newtons per kilogram. Now, what this means is, or what the gravitational field strength is, again, is how strong a object would push you towards it. So just like the electric field strength is how strong an electric object pulls you or pushes you, gravity is how strong a gravitational object will pull you. It doesn't push you, it's gravity. It can only attract. So it works the same way that the electrostatic force does, just with a different value. And we can even draw these invisible field lines around our objects. It's just not very interesting. Earth, of course, has all the arrows pointing towards it, because no matter where you are, what way does gravity pull you? Pulls you towards it. Which way does gravity pull you? Pulls you towards it. You're never going to see, unless it's an incorrect answer, you're never going to see arrows point the other way for gravity. They always point towards because they're always attractive. So it's not very interesting of a question, which is why we don't generally touch on gravitational field strength or gravitational field lines too often. Electric field lines tend to be more interesting because there's positive and negative to it. And even the formula is quite similar. If you remember the formula for electric field strength I just talked about, is this over here. Q and M are very similar. Q is just the factor that affects electrostatic force, while M, mass, is the factor that affects the gravitational force. These two are about the same. The units for G, as I said, can be written as newtons per kilogram. The units for E can be written as newtons per coulomb. Very similar to each other. They do act in very similar ways. So another way of thinking about electric field strength is how it allows us to figure out how much a charged object would accelerate in an electric field. The only caveat to that is you have to acknowledge the fact that mass plays a role in acceleration as well, where this is kind of included in this formula. Okay, I've done a lot of talking about electric fields. Let's do some examples of this now. You're going to notice that the formula is incredibly straightforward to use. Really, the only trick is that often the charge that we have to work with is a particle. So you have to deal with the fact that, I have to look up the charge as 1.6 times 10 to the minus 19. So our formula is E is equal to Fe over Q. My electric field is 2 times 10 to the 2. By the way, you'll notice electric field strengths of around 100 to 1,000 are pretty common electric field strength numbers that I've seen before. They can vary quite a lot, but you often see them in the hundreds to thousands. The force is what we're looking for. We're trying to find the force exerted. And then my charge, again, for an electron is 1.6 times 10 to the minus 19 coulombs. So if I do that math out, I get an electric force of 3.2 times 10 to the minus 17. And again, electric force is just a newtons. And that says draw a force vector on the electron, so which way it goes. Again, electric fields is what would a proton do? A proton would want to move to the right and follow the electric field, but an electron would want to do the exact opposite. So an electron would want to move this way. Again, if this was a proton, it would want to move with the electric field lines. Electrons, of course, being the opposite charge, means it wants to do the opposite thing. So you just have to keep in mind that electrons will go the opposite way of electric field. What's unfortunate is it tends to be electrons that move. As we know from chemistry, electrons are the things that move around. So we'll often find the case that our electric field lines are pointing in the opposite direction of our actual object is moving because we work with negative charges so often. Let's look at a Regents example. This question was on a Regents exam previously. We have electrons are moving through some parallel plates, and you can see it gets deflected, which means that it starts to change the direction it's going over time. And it's asking us to find in which direction is the electric field between the plates. Right away, we can get rid of this A and B. The fact that this is moving, deflecting upwards, means it's not going to the left or not going to the right, because what would those do? Those would make either the particle go faster or slower, depending on the direction. We wouldn't want to, it wouldn't actually change the direction. So it has to be going up or down. Now, because this is an electron over here, and this electron is being attracted upwards, that means that my electric field would be going the opposite direction, because keep in mind, this is a negative charge, which means going the opposite direction of the field. So my field would be going downwards. So it looks like it's going from C to D. All right, got some whiteboard questions. Looks like a lot, but that's because a lot of them are very quick to do. We start off by looking at another electron beam question, looking at which way is it deflecting, how does it work, things like that. And then we go on to answering a couple of questions on protons, doing some math with that. So let's begin going over those. First one says sketch 3 electric field lines between the plates. Don't forget arrowheads. They're very important because we are talking about vectors. If you don't draw arrowheads, then they're just lines, and that doesn't really tell us anything. So again, what would a proton do? So if a proton was in here, we have a positive plate up here, and once we pushed away from that, we have a negative plate down here that's going positive to negative, which it always does. It goes from positive to negative. So that's what a proton would do. Sketch a likely path the electrons would take. Well, they would want to be attracted to the positive plate up here, get away from the negative, or you can think about it, they would want to go the opposite direction of the field lines, so they would start to curve upwards like that. Compare the magnitude of the electric field at point B to point A. Well, as I said before, this is what makes parallel plates so special, is the fact that the electric field is the same between all points of the plates, so they are the same as each other. Okay, now let's forget about the electron beam and move to a proton is added. So the proton moves from A to B to C, so it's moving around. Discuss the magnitude of the electric force on the proton at any given point. Well, because the electric field strength is staying the same, this is true for both electrons and protons, that means that the magnitude of the electric force stays the same at any given point. When it's at A, when it's at B, when it's at C, it's all the same as each other. As long as you're between these two parallel plates, they're going to be the same force. It's going to want to go down to the negative side with the same force. Finally, we have at point B, we have a force of 4.8 times 10 to the minus 16 newtons on it. What is the strength of the electric field at that point? So here's my formula. And we have, let's see, a force of 4.8 times 10 to the 16 newtons divided by, again, I have to look at my reference table. It's 1.6 times 10 to the minus 19 coulombs. If I do that math out, I get 3,000. As I said, 1,000 is a pretty common number we see for here, newtons per coulomb. Okay. Hope that helps. If you have any questions, always feel free to ask. Have a good day, everyone.